Hello everyone, thank you very much for being here with me. Today we continue our discussion on the data structures and algorithms playlist with Quicksort, which is a well-known sorting algorithm. You might have already heard about it. Anyway, before starting, of course, if you are here with me live, remember you have a live chat, so I will always keep an eye on the live chat and try to answer your questions or see your discussions. And if not, you can still ask the questions in the comment section, of course, if you just see this video recorded, or you can find me on LinkedIn and Twitter, and we can talk there as well. Let me share you my screen and continue our discussion on code and try to explain how Quicksort works. And from my point of view is maybe the only sorting algorithm you would need to kind of understand well, because it's, I would say, the most used sorting algorithm. Of course, there are plenty of sorting algorithms out there. There are so many that I don't even think I can say I might be able to name them all. I'm not sure if I actually really know all of them, because there are so many. And well, you can go through them. Of course, they are good exercise, and that's why a lot of students use them to learn, to get the algorithmic ability of thinking. But out of all these, I find Quicksort important for any practitioner because well, it's basically the one used behind the scenes in most of the cases. So when we discuss about methods, and we know today with languages, high-level languages such as Java, where you simply call a method, no sorting already exists there. You will never have to write the algorithm yourself. You will simply just call a method like sort, and everything gets sorted. But you would kind of need to know a little bit what's behind the scenes. And with this lesson, I'm gonna go a little bit through Quicksort and try to make you understand the logic behind the scenes of this algorithm. So with that being said, so what I did is I have already created a project because I don't want to spare inefficiently your time. And the only thing it does is declares an array, which you can see is of integers, and you can also observe that these integers, they are not sorted anyhow, so you just in a random order, and the purpose is of course to sort them. And the only thing that this code does as well is to go through the entire array and print them on a single line with a space in between, so that we can see what is the result when it reaches the output. So our purpose is to put something between the declaration and the initialization of the array and the output, such that the result will be of sorted values. Sorting algorithms can be used to sort any set of values as long as you have a comparison method between the elements. With numbers, of course, you already have the comparison, the mathematical comparison between the numbers, but remember that the same algorithm can be applied with any kind of object for which in a way or another you have declared a way to compare the elements. So usually you do that either by using the comparable or the comparator interfaces, but that's not something in which we are interested at the moment. No, so let's continue. So let's say I want to sort the values using Quicksort. So that tells me that I would need to somehow call a method here that sorts this element. So it should somehow get this as a parameter. What else? Because as you will see, Quicksort, I will immediately explain the logic now, and you will see Quicksort, an easy approach to write it is by using recursivity. You will have to provide it with an interval of values, which in the beginning is the entire array that you want to sort. But as we will continue with the explanation, you will see that Quicksort, what it does, it separates this array that it sorts into multiple partitions into subarrays and it sorts them and recursively applies the same logic until the final array gets completely sorted. So that's why I need the interval here, which in the beginning will be the entire array, but then when I will recursively call the quicksort within itself, I will have to specify a partition, a pivot. It's basically the place where we separate the two partitions being recursively sorted. So then when I'm gonna declare this method, that would be static void quicksort, you can observe that it gets the input value as a parameter, and then it gets low and the high, you can call them, meaning the start and the end, or start and end can also be a good way to name them. And then you will say, please give me the index where I want to partition. We can call it partition index. No, so we will separate the logic of getting a partition in a separate method, and then the purpose is you call for each partition quicksort again, which means you start from low. You have the input, of course, first, and then you start from low, and then you go up to pi, and then you say quicksort, and you get the input again, but then you go from pi plus 1 to the high, which is the end. So that's basically the whole quicksort algorithm. There is only one thing, so that should happen. Of course, the recursivity should stop at some point, and that is when the low is equal or greater than the high. So you cannot continue infinitely with the recursivity. So you will simply have to do that as long as you haven't reached a zero elements partition. So that means we have to add this condition to be sure that we stop at some point with the recursivity, and that is when you don't have what to partition anymore. You don't have anything to partition anymore. So this is how the quicksort looks like. Of course, we still miss something. We still the implementation of the partition method, and that's basically the most important of the things when we discuss about quicksort. So the algorithm itself is just a recursiveness applied on partitioning and ordering the partitions of a given set of values, and it simply looks like this. It's only a few lines of code algorithm, but the heart of quicksort is basically inside the partition method, and there is not one way of writing the partition method. So there are actually multiple known ways of writing the partition, and today I will only cover two of them, which are I think they are basically the most used. In most of the cases you will find either one or the other, but what I want to say is that normally you can even figure out different ways and find out other ways in which you can partition, and depending on how you create the partitions, your algorithm may be more or less efficient. So as you can see from the partition method, we have to get out with an index. So that means that the partition should at least return the index, which is an int. So let me call it partition. So this is basically how it should look like in terms of the signature. And then of course the way it gets the partition, it partitions something. So it partitions the current input that's being sorted, and not only the input, it's partitioning the current partition that you are sorting at the moment. So what that means is that you would need to provide it with both the input and the start and the end of the currently partitioned the current partition to be sorted. So what does it partitioning meaning? So if I'm taking these numbers here, partitioning means find two slices of this such in a way in which you can independently then sort them, which means that, for example, if I'm deciding to partition it into two, just randomly choosing, it will not always work, because then if you sort independently this one and this one, you will not get a finally sorted solution. So for example, choosing a partition, I just randomly chose it, like I separated into half. Choosing a partition here will not be a good solution, because if you then sort this in a way or another and then sort the other in a way or another, you will not end up with a totally, finally, completely sorted array. So you can see that if I did so, I didn't end up with a good result. So the point is finding a way to partition the values into two groups such that in the end, reuniting them, assuming that you have recursively went through again and repeat that all over again through each and every partition, you will end up with a final result that looks sorted. So that's why I say the heart of Quicksort is finding a way to partition the values. And there are multiple ways, and we will talk about two of them, but I will start with the one which is believed to be the easiest to understand. It's called Lomuto partitioning method. And with this Lomuto partitioning method, the whole idea is, I'm going to copy it again because I need to explain Lomuto as well. Is okay, I cannot just randomly choose where to put the index and return it. I need to figure out how to put the element in an order that will create consistent values. And that's, look how it works. You choose a pivot. The pivot can be any number, and again, choosing a pivot, there are multiple strategies, and you can try them all. In some cases you choose the first value, in some cases you can choose the middle value, you can choose the last value, you can choose, there are some cases in which it's called the median of a 3, and there is even the possibility of choosing randomly a pivot. And depending on the set of values, one way of choosing the pivot or another can be more efficient, but I will not go into too many details. I want to be able to finish explaining you the algorithm. So let's just assume we take the last value as a pivot. What I want to do then is I want to go through the entire set of values, and for each of it try to put those that are smaller than the pivot at the beginning of the array, and those that are larger than the pivot at the end of the array, such that I end up somehow with an index separating the values, not necessarily sorted yet, but in a way in which if you'd sort them individually, you would end up with having a good sorted array. So for example, I will start with, I said I will choose the last value, which is 4. And then I can say, I want to put it at the beginning of the array. No, so how can I do that? I just have an initial index, which is 0. And then I say, is 3 smaller than 4? which is the pivot, yes, in that case I have to make sure it is at the beginning. So I put it at the index, which happens to be the same here, okay? And then I increment this index, I make it 1. And then I go further and I say 2. Is it 2 smaller than the pivot, which is 4? Yes, again. So that means I have to keep it at the beginning of the array. So I make it at the beginning of the array by putting it on the current begin index, and then I increment the current begin index. And then I do the same thing with the others until the end of the array. And I say, is 7? No, you can skip over it. Is 1 smaller? Yes, that means you have to put it at the beginning of the array. So I put it here. So basically now I'm switching. I'm switching the one on index 2, which happens to be 7, because I skipped over it, with the one I've reached. So at the next iteration, this is how it will look like, and this one should become a 3. So when you end up with this, so you will basically 8, it's bigger, and then it's 4, so I don't have anything else to do. Look what happened at the end of this iteration. Take a look at it. So 3 is basically the index that will be returned in this situation, because I've parsed through the entire array once, and I just made sure that everything that is smaller than a certain pivot I have chosen is at the beginning. If you see here, 3, where I will split the partition, is basically exactly making sense, because if you would sort independently these two slices and putting them together, because that's basically what you do here, you independently then quick sort again everything, you will end up with a sorted array. No, 1, 2, 3, 4, 7, 8. Look at this. Oh, 1, 2, sorry. 1. Oh man, my keyboard is 1, 2, 3. No, I've sorted independently this one, and then I will sort this one. 4, 7, 8. And I end up with a completely sorted array. Why? Because I've correctly partitioned the array. So that means finding a proper way to partition what you want to sort, meaning whenever independently sorting each of the partitions, when you put them together, you get an entirely sorted array. So this is Quicksort. It's just being able to find a partition rule such that you end up like this, so that you can recursively iterate, through a divide et impera, basically, way of applying the sorting throughout the entire array. So how do I actually write this? Of course, I will do exactly what I've been trying to explain. So first of all, I choose a pivot. We decided together that I can take the last value. So that's input of high. It's the last value in the partition that I'm currently partitioning. I'm partitioning an existing partition. So the initial partition being the whole array. And then of course the partitions become smaller and smaller because you consistently partition them again and recall recursively the quicksort. So remember, here I'm choosing the last element, but you can you may choose basically the pivot in many different ways. So the idea is choosing a value. This will always work because it will always basically compare with one or another. However, depending on how you choose the pivot, depending on the set of values, it might be more and less efficient, but it has to be established if it's more or less depending on what you know that you are partitioning. Sometimes you know how your sets look like and what is the biggest probability to to be in a specific situation where a specific configuration is better or worse. And then of course I can choose that I that I was incrementing, no? And normally I start, because I want to parse all the elements, I start from first -1 so that I increment and then I start with the first initially, something like that. You will see it immediately. So remember, what was the next thing I was doing? I was going through the whole array. So that means I cannot choose an I anymore because I it's already here, but I can just choose a J, and I'm going with the J up to the last. I don't necessarily have to go on the last explicitly, because in this specific way I have already chosen the last as being my pivot, so I can go with an equal to high here, but that would simply mean I'm just always comparing at the last step the pivot with itself, which doesn't really make sense. I mean, it's not helpful, not that it doesn't make sense, but it's not helpful. So once I'm iterating, then exactly what I was telling you, I just try to figure out which are the values that are smaller than the pivot. And if I'm finding such a value which is smaller than the chosen pivot, then I have to make sure that I switch the one on I. First of all, I increment I. That's why I've been starting from -1, because then initially this will be 0, -1, -1, but then when I increment it, it will become 0. So the first value, the first will be 0. So then I can simply just use an auxiliary variable to switch, to swap the two values, the input on the I, with the one on J, and then this one takes the value. So I've swapped basically the one at the beginning of the array with the one I have been parsing. And then at the very last, I'm gonna make sure that I do this partitioning one more time, but this time for the I plus 1. So that would be the last one that I haven't parsed. With the highest. Okay, which is the pivot, which in our case will be with itself, but not in all the cases. So that's, we have to make sure that we consider the case where we've missed the pivot. And then I plus 1 should be basically where you left it over. So I'm now gonna try to redo the algorithm line by line with you on the example. So let me copy this again. And do it one by one. So I initially is -1. And then this is the input. And I will just take one iteration, of course, because the rest, then if you understood how it works on one iteration, then you can figure out that the rest is the same. So I'm just choosing 4 now as the pivot. So pivot is 4 here. and then I will go through the entire array starting with the first one, which is 3, and then I will make the comparison. So this is exactly what we did at the beginning when we didn't have the code. Now I'm trying to explain it once again, and now you also have the code in front of you. So you compare what I'm saying with what you see I've written as the logic. And at the same time, I'm checking if I made everything well, if I didn't miss anything. So I'm iterating 3. 3 is 3 smaller than the pivot. Yes, because 3 is smaller than 4, which was the chosen pivot. So in that case, I becomes 0. And we switch the input of 0 with input of 0, which means that 3 remains on the same place. Which is normal because what we wanted is to keep it at the beginning, but you don't know that you are at the beginning or not. So this algorithm, this partitioning algorithm simply makes sure that whenever you found something smaller than the pivot, you keep it at the beginning. So then it continues with 2. No, because we take them one by one. So we worked on 3, we replaced 3 with itself, just because it happened to be at the beginning of the array. So in this case, again, it makes sense. So I mean, it might look strange. You know, I can understand if you are a beginner that it might look strange that we've just replaced, we've just spent an operation or replacing the same value with itself, but don't think about it like that. Think about the purpose of this replacing is keeping values smaller than a chosen pivot at the beginning and all the others go after, such that you can then partition in those that are larger and those that are smaller. Okay, so look at this. We go with 2. And we have the same because 2 is smaller, so you want to keep it at the beginning. Of course, you cannot replace 3 with it, but that's why you incremented I. Because now I became 0, which means that when we execute this instruction, I will become 1. And that means that this swapping here will swap 2 with itself again, because yeah, it is on the second index, so it just puts the value you reached with j on the value that you reached with I, which is the second value. Which is, again, it may look strange because I've just again replaced the value with itself, but I'm still on the target. I'm just keeping value smaller than 4 at the beginning of the array. That's everything I want to do. That's everything I'm doing. So then I get on 7, and 7 is not smaller, which means that I will just skip over it. See, my algorithm does nothing on the else, which means that if I encounter a value which is larger than the pivot, larger or equal with the pivot, it will simply skip over to the next iteration, which is I'm parsing 1. 1, however, is still a value that is smaller than the pivot. So what do I have to do? I have to again make sure that I swap the 1 at the beginning of the array with the one I'm iterating. So I'm incrementing I becomes 2, and then I'm swapping value 1 with the value on index 2, which happens to be 7. We can see now that we are indeed on the target, because it makes sense 1 has to be in front of 7 if I want to have consistent partitions. So then it means I'm swapping this, and now this is how my array looks like. And then I will continue with 8, which happens to be larger, so again I'm iterating over, and then the entire 4 has finished completely. And then I do one more time, and you can observe here why I chose an I plus 1. I'm making sure that the pivot itself is in the right place, which is the last value. And it's an I plus 1 because if I would have chosen to use I, remember I had this increment here, but now I don't have it anymore. So I need to use the plus 1 to make sure that I don't override an existing value. Basically what this does, it's putting the pivot itself in its right place, meaning it's putting the pivot, which is on the highest index, with the one in I plus 1 here, which means that at the end of this iteration, and which is the final thing we do here, you have the following order of the values. They are consistent because if I'm separating them and I'm independently sorting them 1, 2, 3, 4, 7, 8, then you can see that the final result is a sorted array. So which means that at least up to this point it looks like my algorithm does the right thing. And why am I returning I plus 1? I'm returning I plus 1, which is I is still 2, so I plus 1 is 3. 0, 1, 2, 3 is basically where the next partition starts. Because remember, so I'm separating between low and pi, which is the partitioning index. So I'm taking low up to 3 here, and then from 4 to high. It could have been the same like pi and then pi plus 1 and then starting with pi here. I mean, it's not that important as long as you separate them somehow, but you see that it's exactly the place where you want to split them. So it's somewhere where it's where it makes sense. And if I'm running this now, we should observe that, of course, if I haven't messed it anyhow, then the values should be in order. I did mess it somehow. This is a Stack Overflow, so I forgot to add a condition somewhere. So input low to pi, pi plus 1 to high, low, high. Which I'm not exactly sure what I did wrong here. So line 17, and then this one seems to end up with never being lower than high. So what did I mess it up? If I do it like this, will it be pi minus 1 here? Sorry, minus 1 in this case. I don't think that should be the case, no. Oh, okay, but I'm not totally sure. So let me see, low to pi minus 1 makes a little bit more sense from the numbers point of view, but I'm not sure if it makes sense necessarily for me here. Why I didn't work with pi plus 1? Because it looked like I'm separating still them into a good way. Anyway, I will figure it out. I don't memorize algorithms, so please expect that I might have to figure out things throughout me working. And I don't recommend anyone, of course, to memorize, to learn by heart algorithms. Try to think about them rather than learning them. Okay, but the point is the same. So I've been explaining it correctly. The sorting works. And this is basically what one of the ways in which you can partition the values look like. So it's just trying to choose a pivot and then put at the beginning of the array what is smaller than the pivot and leave everything at the rest of the array. You will always basically like that end up with two partitions that are cohesive, that you can independently then sort and then put together, and it should work. Okay, that's one of them. The second one, and I'm gonna comment this out. And I'm gonna just add a comment here. This is called Lomuto partitioning, which it's simple enough, as you have seen. Now, let's see a different partitioning solution. So we will start from the beginning. And these two that we discuss now, they are not the only ones. Okay, remember that I was telling you there are multiple ways in which you can partition, and I think you can even find your own ways in which you can partition. So as long as you find a way to separate in consistent partitions, then this is basically everything about Quicksort. So this one that we are going to discuss is considered to be more efficient in more situations. It's called Hare or something like that. I'm not totally sure if the pronunciation, if my pronunciation is correct. But in this case, what we are going to do, it's a little bit different. So to find the index of the partition, we are just going to try to find it from the left and from the right and meet somewhere in the middle. So I'm gonna start with an I going from the first value to the last, and with a J going from the last value to the first. When I'm going from the first value to the last, I'm trying to figure out if I found an element which is smaller than a given pivot. So again, we will have to choose a pivot, and for the sake of the example, let's say that this time the pivot is the lowest element. Okay, so in that case, it will be 3 in my case. So what I'm gonna do is I'm gonna try to find the one which is smaller than 3, and it will happen to be 2 in this case. And then when I'm going back, I'll try to find the one that is larger than 3, which will be 4. So at the first iteration, in my case, I will turn up to be 1, while J will turn up to be 5, no? Because it's 0, 1, 2, 3, 4, 5. And then I will say, did J become smaller than I? If not, it means I didn't find yet a partition. So I'm gonna continue like that, swapping the elements when I didn't find a partition. So I will swap them until I find basically the right partition, until J is smaller than I. So let's do the same thing. Let's try to write the code and then verify ourselves by discussing the code line by line again on the example, exactly as we did with the previous Lomuto way of partitioning. I'm gonna start very similar. I'm gonna choose a pivot, but then I will have an I which will be low -1, because I'm starting from somehow from before the array, no? And then I have a J, which is high +1, because I'm starting again from after the array, going back, so that when I do parse the values, I'm taking all of them. So then I'm gonna just do an while and say, while input of I is smaller than the pivot, continue incrementing this. So I'm going from before the array up to the array, trying to figure out where I put the I index. And then of course, the same thing with j, but j is going backwards. So for j I will have to decrease, and then I will decrease it if the value is bigger than the pivot. Remember, when we go from left to right, we check for the value which is smaller and increment until we found a larger value. And then on the other way around, we stop only when we found a smaller value. If we are in the situation where j is smaller or equal than I, we return j, meaning we found the pivot. And then of course, if we didn't go, or if we didn't return, then we will step over, and that means we are not yet in the situation where we found the partition, the right partition. It means the two elements we found are not in the right place. So we'll have to swap them similarly as we were doing here. Using an auxiliary value. So I'm just copying because I'm lazy. Yeah. We're just swapping them exactly as we were doing here, no? And then the point is, you have to do this continuously, and you don't know exactly when you will reach that. So what I'm gonna do is I'm just going to loop indefinitely through this until we are in the situation where j is smaller than I and we found a pivot. And that's basically it. I'm gonna test it first just to make sure I didn't make any other mistake, because you see it happens again. I'm not. So now I'm again on this, but that's probably because hopefully because I'm somehow on the other side like this. Let me see. Okay, so for this case, it seems to have something with the index that I'm not doing right here, but I'm not gonna, I mean, it's a very small detail and I'm not gonna lose now time debugging into it. But the point is, yeah, it's the same thing, okay? We found the right partition, and then if we do that, then you will end up with a good result. If you look at this, basically it's the same thing. We can now do the same thing we were doing. So I will just take the value again and take them line by line, trying to explain them again, but on this new method. So what do we have here is I have an I, which is -1 at the beginning, and I have a j, which is 6 at the beginning. Why are they -1 and 6? Because low is 0, so 0 minus 1 is -1. High is 5 because it's the last index, so j should be 6. And then you just follow this. You will see do increment I while you didn't find yet a value that is larger than the pivot, because the value that is larger than the pivot doesn't fulfill anymore with the condition of being at the beginning. So 3 is the pivot. 3 is not fulfilling. So then the first one is it's a little bit, I think, different than I explained it initially. So that's why I take it again, because it sometimes in my mind it's not exactly what it looks like when after I write the code. I'm not sure if you are the same as me here, but that's how it happens to me. So this condition now, because the pivot itself is 3, 3 is more than 3 is false and continues, I'm gonna go to the j and say j is larger. So is 4 larger than 3? Yes, so this becomes 5, and then it stops. No, it doesn't stop, so because j is larger than 5, it continues. It continues to the 8. 8, it's still larger than 3, so 4 is larger, 8 is larger. It decreases, and then it decreases again, because 8 was larger, it becomes a 3, but it reaches 1, which means that it skips over this one, because 1 larger than 3, it's false. But being that I is 0 and j is 3, the condition doesn't match here. That doesn't match because it isn't met because 3 is not smaller or equal than 0. So it means we have to swap the values on 0 and 3, and then we continue with the iteration, something like that, no? So that means 1 and 3, like that, will be the next. Or maybe it was better if I was doing it like I did in the previous 1 and 3. Okay, and then it's a while true, so it goes back and it continues, and it says I becomes 1, and then is 2 smaller than the pivot? Yes, then it continues with 7, which is the one that basically is not matching now, because 7 is larger than 3. Be careful that the pivot is still 3. Okay, here it was actually. And then it goes with the 3 itself. So j becomes the same, and then it continues again. And I think I missed something, because I don't think I end up here with the correct partitions. So you may want to take this again and see if I messed something when I try to do them line by line. But in the end, you should still end up with something like 137. I think it does actually one more, and then it's fine. So 137. So yeah, the next one is basically, it should be something like 137. And then I think the index should actually be 3. So I did mess something here, because I think it should be something like that in the end, 3 and 3, which is basically the exactly two subpartitions, consistent subpartitions that we need. Anyway, you can take it line by line, and you see that I'm right. And that's basically it. So that's how you'd write Quicksort in two different ways, I would say. But remember that the two different ways are not given by the algorithm itself, but the partitioning. So the algorithm just says, just find the way to split into two different partitions, which can be independently sorted, such that when you sort them and you reunite the results, you end up with a complete sorted group. The heart of the algorithm is finding the way to partition, and we discussed about these two, Lomuto and Hwari, which are the two main. I think Hwari was actually the first one and the initial one knowing in the algorithm, while this one has been discovered afterwards. And I think Hwari is the one that you will use in most cases. Cool. Yeah, I think hope at least that it made sense, and I'm not gonna spend more of your time. This completes the Quicksort, and I do recommend you find a few more minutes to figure out if you have any questions, and try to figure out how the algorithm works by debugging over the whole code. As usual, I will put my code on GitHub after the event, so you can take it yourself. You don't have to write it by hand. And if you have questions, As usual, please remember you can find me on LinkedIn and Twitter, or you can leave your questions in the comment section and I will try to answer them. Thank you very much for being with me here. I'm waving goodbye and hope to see you soon. Until then, have an excellent time for learning.